Hello, everybody. My name is Philip. I'm a PhD student with Professor Felix Herman at Georgia Tech. And I'm going to talk about what we did for seismic imaging in the cloud. I just briefly want to acknowledge my co-authors. So this was work that was done with Charles Jones from Osaki. And then I would thank Microsoft Azure a lot. So this was a project that was done with Microsoft. And we could really only do it not only because they gave us access to the platform, but they also gave us access to the knowledge of all these people that work with us on that. So thanks very much to Azure. So in this talk, I'm going to look at a specific application and talk about how can we bring this application to the cloud. And I'm specifically saying specific application because really, I mean, there's different ways how you can bring software to the cloud. And in this case, we really want to take a look at our application and analyze what are the mathematical properties, what are the things that we can take advantage of when we want to deploy the software to the cloud. So in this specific case, we're going to look at seismic imaging. So here we have the least squares migration objective function, and we want to take advantage of the fact that the function value is embarrassingly parallel to compute. So I mean, traditionally, when we write our software, I mean, for the last 30 or 40 years, pretty much all the software that we have in oil and gas was developed for high-performance computing clusters. I mean, this is kind of our home turf. This is what we know. This is what we know how to do. And I mean, it's important to remember that all the software we write, there's always some inherent assumptions when we write our software, namely that there's really fast inter-node connections, that the HPC clusters, they're pretty reliable, at least compared to the cloud. The nodes usually don't go down very often. And when we write our software, obviously, this is kind of the things we just take for granted. But in the cloud, it's not necessarily that you have all these things. And then on the other end, there's, of course, some problems like high upfront costs that if you have to purchase a cluster. And then the second thing I want to point out is that usually, almost always, when you have to buy a cluster, you have to compromise on the hardware because different people are going to use it. Different people want different things out of the cluster. So almost always, there have to be compromises. So now in the cloud, I mean, I guess the biggest advantage is that you have the full flexibility of all the hardware that is available. It's pretty much unlimited in what you can scale up because, I mean, the data centers run by Azure or AWS are huge. And so, I mean, I just want to briefly point out, I don't really want to go into cloud versus on-premise HPC, which one is better. I mean, I don't think it's kind of the wrong question to ask. And of course, I mean, for some applications, definitely HPC on-premise would be the way to go. In other cases, where you maybe want to supplement your on-premise resources, or you have a very varying workload, the cloud is the way to go. So again, I don't really want to get into that. I just want to point out that the cloud obviously has some advantages that you don't have on HPC on-premise clusters, like mainly the flexibility, and that you don't have to pay any upfront costs. You can just log in, and you only pay for what you use. On the downside, of course, there are some issues like slower node connections. It's a little bit of a, obviously, generalization here, but I mean, the cloud providers have invested massively into the HPC hardware, but many of the basic cloud nodes, you're typically not as fast in terms of the interconnect, and the mean time between failures is usually larger. So now, if you've decided you want to go to the cloud and you want to port your software to the cloud, so the straightforward thing you could do is you say what's called the lift and shift approach. So you take whatever software you ran in your HPC cluster, and you don't really do anything with it. You spin up then a cluster of instances in the cloud. So you spin up some instances. You set up an MPI cluster. You can have some type of network storage or parallel file system, and you can run your legacy Fortran C code that runs with MPI. And I mean, you can definitely do that. Almost no work required in making this happen. But the problem is, of course, in the cloud, that you're really kind of pretending you have this, but you don't actually have this. So one of the things is you always have to wait until those clusters are started up. And there's a potential problem that if you have idle instances, you're always going to pay for that. So here I want to introduce you to a different approach, what we call the serverless approach, where we say, OK, we're going to forget about what we did on the HPC cluster. Now we're going to re-engineer our software. We're going to look at how can we take advantage of technologies presented by the cloud, for example, like massively parallel batch computing, and take advantage of this technology, and then combine that with software like DeVitto, where you can use automatic code generation to generate code that either runs on a CPU with OpenMP or multiple nodes with MPI or even now on a GPU. So in this case, you're able to, okay, it's just like a number we threw out there, but you're definitely able to make some significant cost savings, and you address some of those pitfalls of cloud computing like resilience issues. So the specific application I'm interested in is seismic imaging, where we want to minimize the misfit between synthetically modeled data and observed data. And the key point here really is that we have to compute this as a sum over all source locations. And of course, even though evaluating this for one source is very expensive, doing this for multiple sources is embarrassingly parallel to compute. So you want to compute this gradient for a subset of sources, and then we have to sum all those gradients and use it to update our image using some given optimization algorithm, whatever you prefer here. So now the key idea is, since these computations are embarrassingly parallel, we're going to take advantage of a service called Azure Batch. So Azure Batch is an embarrassingly parallel, massively parallel job scheduler where you can submit jobs to a job queue, and then Azure Batch is going to take care of provisioning the resources it takes to get this job done. So in our case, we're going to have, say you want to compute the gradients for 1,000 source locations. You say, okay, these are 1,000 jobs. Compute these 1,000 gradients, and you give that to Azure Batch, and at that point, you don't have to have anything running. You're not paying for anything. And then Azure Batch is going to take care of launching the computational resources to get that done, and once it's done with that, it's going to automatically scale down the resources afterwards. So the idea is that Azure Batch takes care of all the scheduling, resource allocation, and making sure that you're only running what you're actually using at this point. And so one of the advantages is that all these jobs, they run fully individual of each other, but you still have the possibility to do domain decomposition and use, say, multiple nodes per job. So you can really have like a cluster of clusters where all these clusters are fully independent of each other. So if one of these goes down, which, I mean, we all know that happens sometimes, that does not affect any of the other jobs here. And then I just want to briefly mention the software. So of course, it's possible that you run your legacy MPI code on this, and Tim Lin from SQP actually did a terrific job doing that, kind of adapting like a classic MPI code. But in our case, we're going to use DeVitto, and Azure Batch runs all these jobs as Docker containers. So in your Docker container, you have all the control. You set up what kind of OS do you want to use? You put your software in there. You can test that locally on your computer, and it's very easy and convenient to set up. And once you've done that, you're going to deploy that to Azure Batch, and we're going to use DeVitto to automatically generate the C code to do the wave equation solves. So I want to briefly mention Azure Shipyard. So Azure Shipyard is software that Microsoft developed that sits on top of Azure Batch. Because you have to set up all these Docker containers, and it's possible, for example, to do MPI jobs with InfiniBand, but you have to set up these Docker containers with InfiniBand, which is a little bit of a daunting task. So Batch Shipyard already has a lot of templates, and then you can fill in parameters using like a JSON file that's very convenient to set up. So this is what we used in our case here. Oops, wrong direction. Okay, so now we have this batch computing system that can compute all these gradients for us in parallel, but then all these jobs, they cannot talk to each other. But we want to now use some of the gradients that are computed there, and then use those gradients to update an image or run some optimization algorithm. So the way we do this now is where now this event-driven comes in. So you have all these jobs here that run independently of each other, and they all compute the gradients. And the gradients, usually, they're not finished at the same time. So some are faster, some are quicker. So now we have what's called this message queue that collects messages. So if one of these jobs is done, they're going to send a message to a queue and say, I computed the gradient with this job identifier. And then they're going to store the gradient. In Azure, it's called Blob, which is Azure's object storage. So now up here, we have this messaging queue that collects the names or object identifiers of the gradient that's been computed. And once you add a gradient to this queue, what automatically happens is you're going to spawn these Azure functions that are going to take care of summing these gradients. So if you don't know what an Azure function is, think of it that way. Think of it, you have some Python code, for example. You upload that to Azure, and now it sits on Azure. It's not doing anything. You're not paying for anything. And Azure is going to run that code in response to an event. In this case, an event being you finish a gradient commutation. Gradient is saved in this blob, and now you want to sum multiple gradients. So once you have at least 2 gradients in here, these Azure functions are going to run code, and this code is just going to read these files from the blob, sum them, and write them back to the blob storage. And you can sum up to 10 gradients in this case, and then write them back, and then you're going to repeat that recursively until all jobs are done and all gradients have been saved into a single file. So the advantage here is that this happens asynchronously. So this starts as soon as 2 gradients are have been computed. You already start summing these gradients. So hopefully by the time the final gradient is computed, you're already done summing most of those files, and now you don't really have to wait a very long time. And also you can do this in parallel because you can have multiple Azure functions running in parallel. Right. That basically just sums up what I iterated. So another advantage is that these Azure functions, you don't have to provision the resources, and they're usually the resources used by Azure to run these Azure functions are cheaper than if you have to launch like a big VM. And then I briefly want to mention that this is truly a multi-platform approach. So if you look at this and say, OK, I'm not using Azure, I want to run stuff on AWS. So initially, I developed all the software for AWS, actually. And then Microsoft became really interested in this. So they invited us to port this idea to their platform. And it was actually very simple to do that. So this batch processing technology, you have that both on Azure and AWS. The Azure functions, the direct equivalent is, of course, Lambda functions. So all these technologies, you can do all this on either of these platforms. So now I want to talk about this 3D imaging example that we did with Azure. So after we ported our technology, they said, we want to run an imaging example with you to see if we can scale it up. So we have a model here that's 10 by 10 kilometers, 800 by 800 by 350 grid points. So that's roughly, I guess, 280 million grid points. We're going to have 1,500 randomly distributed ocean bottom nodes, and we have a dense source grid of 799 by 799. But we're going to use source receiver reciprocity to actually only model 1,500 shots. So this is the dense source vessel grid. This is the OBN, random OBN receiver grid. But then for modeling, we're going to flip that, so we only have to model 1,500 shots. So this is the setup that we used in Azure. We used the E64 VMs. We only had access to 100 machines at the same time, and we used 2 machines per gradient, and then used a menu decomposition to solve 1 gradient on 2 VMs, because we need access to enough memories that we could save the wave fields in RAM. And the only restriction here is that we wanted to stay below $15,000, so we were able to run this example with $11,000. So here on the left, I plotted the runtime as a function of the job ID. So we had, like I said, we have 1,500 sources. The offset was limited to kind of decrease the domain size, so jobs that are more on the edge of the model are a little shorter. But the key point was that with Azure Batch, because you have this automatic scaling of the resources, that you only ever paying for what you're actually using. Whereas if you had done this on a fixed cluster, where you have a fixed amount of resources, you're going to have idle time because you have to wait until all those gradients are computed before you can go to the next iteration, because you have to sum the images, all the gradients, to update the image. So for example, so here we plot the idle time as a function of the cluster size. So if you have a cluster with only one node, obviously the idle time is 0 because one node does all the computations. But now if you increase the pool size, you're going to distribute all those 1,500 jobs. But at the end, after you distributed the final jobs, you always have to have some workers sitting there until all the computations are finished. So of course, like if you go to maybe 1,400 nodes, then most of the work will be done after one round. But then 1,300 nodes have to wait until the last 100 nodes finish their computations. But with Azure Batch, you don't have that issue because you have this automatically up and down scaling that you never have to pay that. And I mean, I want to point out, to be fair, that you can also achieve that with a cluster on Azure or AWS when you use autoscaling, but it's definitely more work to make that happen where it's just kind of built in by default into Azure Batch or AWS Batch. So here, for example, we have something to visualize that. So here you have a cluster of 20 nodes, and you don't actually have to wait until all nodes are up before you can start your job. So you're not paying for all the nodes that are already sitting there, and you don't have to wait for them. So here, for example, we have some nodes that are already ready. So the gray ones are idle. The green ones are already doing computations. And the yellow and the purple ones are in the process of spawning up. So then you see the next here that Azure Batch then assigns a workload to these ones. And now you're doing computations on these ones. And then after you're done computing, Azure Batch will scale this automatically back down. OK, so now I have some imaging results. So now I'm going to step through depth. So here you can see at the very shallow part, obviously, we have the imprint of the sources. And you can see this very nice random imprint of the sources here. And then as we step down, obviously, those artifacts become less and less. So full disclosure, this is just an inverse crime. We generate our own data with the same kernel that we're modeling. That was not really the point to prove here. It was really more, here's a budget. Can you guys actually run this and scale this up? And I also want to point out that the scale and the number of grid points and the number of PDE solves that we did here was mainly constrained by just time and Azure credits. But there's, in principle, nothing is stopping us from taking this and run and scaling this up like an order of magnitude. Right. So briefly, the frequency spectrum was not super high, but it was like in the range between 10 and 30 hertz. But we had some energy up to 40 and 50 hertz as well. Oops. So yeah. So the key message I want to bring across is that if you move to the cloud, there's definitely some opportunities there. If you're expecting you're getting the same as you did on an on-premise cluster, you're probably going to be disappointed. But you should realize that there's other opportunities and technologies that you can take advantage of. For example, is serverless or batch computing, event-driven computations, object storage that you don't really have available on a traditional cluster, but the cloud really offers a great opportunity. But then, of course, you have to take a little bit of a look at the application and redesign and kind of break down your monolith and really adapt this software to the platform. All right, so thank you for your attention. And we have a full preprint with a full performance analysis and cost analysis on Archive. Thank you.
We have time for a couple questions.
So I guess we've had challenges with Azure Functions actually scaling to the Event Hub and actually handling all the messages that were going into the Event Hub. What kind of challenges, I guess, how many partitions did you have in your Event Hub, and what kind of challenges did you run into as far as that kind of scaling? Was the Azure function able to keep up with the messages in the Event Hub?
That was definitely a challenge. At the end, we got it to work. So what made it, I think, work in this case is that you never have like 1,000 messages at the same time. So the time period over which those messages come in are like maybe half an hour. It's almost constantly a few come in, but it's never a very large bulk at the same time. But there's always, yeah, I mean, some messages always get lost, so you kind of have to take that into account as well. But yeah.
Any other questions?
So needless to say, you told us about the things that worked really well. Now, just between the two of us, what did not work so well? What were the challenges?
I mean,
was it the tuning of the code to?
The challenges are that you have all these different components, Azure Batch, Azure Functions, and you really, if they don't go together seamlessly, then there's going to be problems. So already, yeah, it's not that easy to use initially, and the learning curve, if you use all this stuff, is very steep. So that might take definitely some time to use this.
Do you have a gut feel for the effort required to do the port or the rethinking of the algorithm?
To the what?
Just the effort required, the relative effort.
So it took me a few months to get this done the first time. So on AWS on AWS, and then once I did it once on Azure, then it was more of a matter of weeks. But I'm not a software engineer, so if you put some really smart people on it, that might be definitely quicker. But it's definitely, it takes an effort between like domain specialists, HPC people, cloud people, to really force them to sit in a room and figure this out together. It's definitely not an easy task.
Thank you.
Good job.